Some locomotives solved impossible problems with elegant engineering. Others pushed boundaries so far ahead of their time that nobody appreciated them until it was too late. From turbines that spun at 6,000 revolutions per minute to machines that recycled their own steam in the desert, these are 15 forgotten locomotives from the 1930s that were actually brilliant. Let us count them down. Number 15, Baldwin 60,000. In 1926, Baldwin celebrated their 60,000th locomotive by building something special, a 3-cylinder compound that operated at 350 pounds per square inch when most ran at 200. One high-pressure cylinder between the frames fed 2 low-pressure cylinders outside, squeezing every ounce of work from each pound of steam. Thermic siphons improved circulation. The compound arrangement cut coal consumption by 20% while pulling 1,000 tons at 60 miles per hour. Pennsylvania Railroad tested it in 1940 and found the performance impressive. But 3 cylinders meant 3 sets of valve gear, 3 opportunities for failure. Maintenance crews spent more time adjusting valves than running trains. In 1936, Baldwin added streamlined shrouding that made routine maintenance nearly impossible. Need to adjust a valve? You had to remove 50 pounds of sheet metal first. The locomotive toured America in 1933, demonstrating compound efficiency. Railroads watched, nodded politely, then ordered simple expansion locomotives because 3 AM repairs mattered more than fuel savings. Baldwin 60,000 ended up at Philadelphia's Franklin Institute in 1933 as a static display, where it remains today. It proved 3-cylinder compounds could work, but working and being practical were not the same thing. Number 14, the LMS Turbomotive. In 1935, the London, Midland, and Scottish Railway built a passenger locomotive powered by steam turbines instead of pistons. Engineer William Stanier mounted a Princess Royal boiler on a chassis containing a 2,000 horsepower forward turbine and a 1,000 horsepower reverse turbine. The turbine spun at 6,000 RPM, driving the wheels through double reduction gearing. Above 40 miles per hour, the turbomotive was remarkably efficient, quieter than any piston engine, and completely vibration-free. Crews reported it felt like driving an electric locomotive. Test runs showed fuel consumption dropped 15% compared to conventional Pacifics. But turbines need steady speeds to work efficiently. Stop and go. Operation killed efficiency completely. Below 30 miles per hour, fuel consumption doubled. The gearing added significant mechanical losses. Maintenance required specialized turbine knowledge most steam fitters lacked. The turbomotive ran from 1935 until 1949, when replacement parts became prohibitively expensive. LMS rebuilt it as a conventional Princess Royal in 1952. It proved turbines could work in locomotives, but diesel-electric transmissions offered the same benefits with better low-speed performance and simpler maintenance. Brilliant engineering applied to the wrong problem. In 1935, Germany's Deutsche Reichsbahn partnered with Henschel to build streamlined tank locomotives specifically for high-speed express service. The Class 61 featured a 464 T-wheel arrangement with massive 2,300mm driving wheels, optimized for the 176 kilometers between Berlin and Dresden. Wind tunnel testing shaped every curve. The locomotives achieved certified speeds of 175 kilometers per hour, with trials hitting 185 kilometers per hour. Lightweight construction principles kept service weight to 129 tons. What made them genuinely innovative was bidirectional operation at equal speeds. The streamlining worked both ways, eliminating turntable time at terminals. For the Berlin to Dresden run requiring 100 minutes, the Class 61 hauled 4 car trains at an average of 106 kilometers per hour, including stops. But they carried only 5 tons of coal and 17 cubic meters of water, enough for one direction. Terminals needed complete reprovisioning infrastructure. World War II killed expansion plans. Only 2 were built. The second unit, 61002, survived, and East Germany rebuilt it in 1960 as Locomotive 18201, proving the design's soundness. The Class 61 showed tank locomotives could match tender locomotives for high-speed work, but infrastructure requirements made them economic non-starters. Number 12, the Polish PM36. In 1937, Poland unveiled a streamlined 282 locomotive that won gold at the Paris World Expo, then was largely forgotten outside Poland. The PM36 one combined Art Deco streamlining with genuine technical innovation. Designer Stanislaw Kilbasinski created a locomotive capable of 140 kilometers per hour while pulling heavy express trains between Poland and France. Wind tunnel tests at Warsaw Technical University shaped the nose profile and the skirting to reduce drag by 18% at speed, yielding fuel savings of nearly 10% on high-speed runs. The boiler used Polish-developed superheating technology that achieved temperatures 50 degrees higher than standard European practice, improving thermal efficiency significantly. Roller bearings on all axles reduced friction. The mechanical stoker fed coal automatically, rare in European practice. Crews loved the cab design, with all controls within easy reach and excellent forward visibility. But only two were built before Germany invaded in 1939. The Nazis captured both and converted them for military use. Neither survived the war. Poland had designed a world-class express locomotive that could have dominated European routes. Instead, World War II erased it from existence before it could prove itself. Post-war reconstructions show what might have been, but the original brilliance died in 1939. In 1937, the Soviet Union celebrated the October Revolution's 20th anniversary by building two of the most aerodynamically refined locomotives ever designed. Kolomna Locomotive Works produced the 232K series with a 4/6 four-wheel arrangement shaped entirely in wind tunnels. Soviet engineers spent months testing scale models, optimizing every curve. The result looked like a bullet on rails, smooth from pilot to tender. Test runs demonstrated speeds exceeding 150 kilometers per hour, and one trial hit 170. The locomotives entered service on the Moscow to Leningrad route in 1938, where their speed and style impressed passengers. High-pressure boilers, comprehensive superheating, and balanced reciprocating masses allowed sustained high-speed running. Maintenance records showed reliability matching conventional designs despite the complex streamlining. Then World War II arrived. Production stopped immediately and resources went to tank production. The streamlined shells proved difficult to maintain during wartime. Both locomotives survived but lost their shrouds during the war. After the war, one operated until 1957, stripped of streamlining, proving the base design's soundness. The 232K showed Soviet engineering could match anything Western Europe produced. Bad timing killed series production. Number 10. South African Railways Class 25. Crossing the Karoo Desert, South African locomotives faced one impossible problem: water. Every drop had to be hauled hundreds of kilometers through territory where wells ran dry. In the early 1930s, South African Railways engineer A.G. Watson proposed locomotives that recycled their own exhaust steam. The Class 25 condensing locomotives emerged, using a 4/8 four-wheel arrangement and pulling tenders so massive they dwarfed the engines. These were true condensing machines. The tender was a mobile power plant containing 6 steam-driven fans, over 3 kilometers of radiator tubing, and full condensing equipment. Exhaust steam flowed into the tender where the fans forced it through radiator tubes. Air cooled the steam back into water, ready for reuse. On good days, the system recovered 90% of water, extending range to 800 kilometers between stops. But radiator tubes clogged with mineral scale. Fans required constant attention. The tender's weight wore down rails. Maintenance logs from the 1960s read like horror stories, crews battling fouled condensers hundreds of kilometers from help. The Class 25 operated for decades because water scarcity left no choice. When diesel electrics arrived, the condensing locomotives vanished almost overnight. They proved you could recycle steam, but complexity made diesels look simple. Number 9. Milwaukee Road Class A Hiawatha. In 1935, the Milwaukee Road needed something fast to compete with Burlington's Zephyr. What they got was a 442 Atlantic that could hit 120 miles per hour, and it did so regularly. Engineer William Winterroad designed the Class A for sustained high-speed running on the Chicago to Minneapolis route. The locomotives featured 84-inch driving wheels, the largest ever on an American 442, giving tremendous speed potential. Streamlined shrouding reduced drag, and oil firing eliminated coal handling delays. The results stunned the industry. On May 15, 1935, locomotive number 2 hit 112.5 miles per hour, then maintained 100 miles per hour averages in regular service. The Hiawatha trains covered 410 miles in 6.5 hours, averaging 63 miles per hour, including stops. For 1935, this was breathtaking. But here is what made them brilliant. The Class A locomotives were small, light, and simple. No articulation, no complications, just sound engineering pushed to its limits. Maintenance costs stayed reasonable. Crews loved them because visibility was excellent and handling predictable. The Milwaukee Road built only 4 from 1935 to 1936. They operated until 1951. Replaced not because they failed, but because diesels were cheaper. The Class A proved steam could match diesel speed, but economics mattered more. Number 8. Southern Pacific AC4. In 1928, Southern Pacific took its mallet designs and simplified them into something brilliant, the AC4 class cab forward. Previous articulated locomotives used compound expansion that required constant adjustment. The AC4 eliminated compounding entirely. It used 4 identical cylinders, all at the same pressure, and maintenance became straightforward. The cab forward arrangement solved a problem that killed crews. In Sierra Nevada tunnels and snow sheds, exhaust smoke from conventional locomotives accumulated in deadly concentrations. Crews staggered out gasping. Moving the cab ahead of the boiler let crews breathe clean air while exhaust vented behind. Oil firing made this possible, with fuel piped forward from the tender. The AC4 developed 116,000 pounds of tractive effort, enough to haul heavy freights over Donner Pass grades. The 4-8-8-2-wheel arrangement distributed weight well, reducing rail wear. Baldwin built 25 AC4 locomotives from 1928 to 1929. They proved so successful that Southern Pacific ordered cab-forward locomotives exclusively until 1944, eventually owning 256. The AC4 established the pattern, simple expansion, cab-forward, oil burning. Later classes added power and refinements, but the basic concept remained unchanged for 16 years. Sometimes the first production version gets it right. In 1940, French engineer André Chapelon took 25 aging Paris-Orléans Pacifics and rebuilt them into 480 freight haulers that achieved thermal efficiency matching early diesels. Chapelon was obsessed with thermodynamics, studying every aspect of steam flow. The 240p rebuilds featured enlarged steam passages, sophisticated compound expansion, double Kyle-Chap exhaust systems, and comprehensive superheating. The results were staggering. The rebuilt locomotives developed 50% more power while burning less coal. On the Paris to Lyon route with its 1% grades, the 240p hauled 750-ton trains at speeds the originals never managed. Test data from 1941 showed thermal efficiency of 12%, remarkable for steam. But here is what made them brilliant. Chapelon achieved this through understanding, not brute force. The compound expansion used steam twice. The Kyle-Chap exhaust maintained draft with minimal back pressure. Enlarged passages reduced throttling losses. World War II interrupted everything. The locomotives served through occupation, then post-war electrification made them obsolete. All were scrapped by 1950. Chapelon's work influenced engineers worldwide, but the 240p locomotives themselves vanished. They proved steam could match diesel efficiency, but they arrived exactly when nobody wanted to hear it. In 1933, Burlington Route commissioned wind tunnel tests at M1T to develop a revolutionary streamlined steam locomotive that could match diesel efficiency. Engineer Ralph Budd wanted to prove steam viability. The prototype design featured a completely enclosed, streamlined body, air-smoothed from pilot to tender. The boiler operated at 450 pounds per square inch, with sophisticated feedwater heating. A 3-cylinder arrangement used poppet valves for precise steam admission. Everything was optimized for sustained high-speed running. Test calculations suggested the design could match diesel performance while burning less fuel per mile. But construction revealed problems. The enclosed body trapped heat, making cab temperatures unbearable. Maintenance access was nearly impossible. The high-pressure boiler required exotic materials. Then the diesel Zephyr ran its dawn-to-dusk demonstration in May 1934, covering Denver to Chicago in 13 hours and capturing national attention. Burlington management looked at diesel reliability and steam complications and made a decision. The steam locomotive never left the drawing board. The diesel Zephyr entered service in November 1934, and streamlined steam dreams died. Sometimes brilliance is not enough when something simpler works just as well. Number 5. LNER W1 Hush-Hush. In 1929, Britain's LNER unveiled a locomotive so experimental they swore everyone to secrecy during development. Chief Mechanical Engineer Nigel Gresley designed it around a revolutionary water tube boiler borrowed from naval practice, operating at 450 pounds per square inch when standard locomotives ran at 180. Higher pressure meant more power from less steam. Yarrow and Company built the revolutionary boiler. The streamlined casing gave it a futuristic appearance that drew crowds, but the W1 was a nightmare in practice. The water tube boiler required obsessive water treatment. Any impurities caused scaling that blocked narrow tubes. The boiler foamed constantly, carrying water into the cylinders. Maintenance crews spent more time fighting the boiler than running trains. High-pressure steam created superheating problems. Engineers added reheating equipment, which increased complexity. Test runs showed disappointing performance. The boiler could not maintain pressure under heavy loads, and the locomotive spent more time in shops than on rails. In 1937, LNER gave up. They removed the water tube boiler and installed a conventional one. The rebuilt locomotive ran successfully until 1959, proving the basic design was sound. But the revolutionary boiler remained an expensive experiment that taught costly lessons. Number 4. New York Central Commodore Vanderbilt. In 1934, industrial designer Henry Dreyfuss streamlined New York Central Hudson 5344, creating one of American railroading's most distinctive locomotives. The Commodore Vanderbilt represented genuine aerodynamic experimentation. New York Central ran wind tunnel tests at Case Institute of Technology, testing scale models. The final design featured a bullet-shaped nose, smoothly fared shrouding, and shaped skirting that reduced drag by 28% at speed. The shrouding integrated with ventilation systems and access panels, so the locomotive could be serviced without removing major sections. Test runs showed measurable fuel savings. At speeds above 60 miles per hour, the aerodynamic improvements reduced coal consumption by 12%. The firemen reported that improved draft made firing easier. However, the streamlining made the locomotive heavier, which reduced acceleration. The skirting restricted visual inspection of the running gear. Most importantly, the styling was distinctive but not beautiful. Passengers and management preferred later Dreyfuss Hudsons with a more refined appearance. The Commodore Vanderbilt ran until 1952, then went to scrap. The aerodynamic data it generated influenced later streamlined locomotives, particularly the J3 Hudsons. Sometimes the prototype teaches lessons more valuable than its own service life. In 1934, Union Pacific unveiled a revolutionary streamlined train set that looked like science fiction. The M1000 featured a distillate-powered engine, articulated lightweight construction, and aerodynamic styling that captured America's imagination. Engineer William Jeffers was obsessed with weight reduction. The three-car train set weighed just 85 tons, less than a single conventional passenger car. Aluminum construction throughout saved weight without sacrificing strength. Articulated design meant cars shared trucks, eliminating redundant wheel sets. The power car featured a 600 horsepower Winton distillate engine, running on low-cost fuel refined from crude oil. Streamlining came from extensive wind tunnel testing at the University of Michigan. The M1000 set a speed record of 120 miles per hour during testing and then entered regular service on the Portland route. Problems emerged immediately. The distillate engine proved unreliable. Fuel savings vanished because of constant maintenance. Articulated design made the train set inflexible. You could not add or remove cars. Lightweight construction also meant rough rides. By 1941, Union Pacific converted the M1000 to diesel power and then scrapped it in 1942. but its innovations influenced every streamliner that followed. The M1000 was too radical, but it showed the way forward. In 1939, the Pennsylvania Railroad built the longest, most powerful, most impractical passenger locomotive in American history. The S1 was Raymond Loewy's streamlined masterpiece, a 6446 duplex drive monster, measuring 140 feet long and developing 6,900 horsepower. Everything was excessive. The duplex drive split power between two sets of driving wheels, allowing huge power without articulation. Streamlined shrouding enclosed everything in Art Deco curves. 4 massive cylinders generated thrust that could rip couplers off freight cars. The S1 spent its first year on display at the 1939 New York World's Fair, where millions saw the Pennsylvania Railroad's vision of the future. Then reality arrived. At 140 feet long, the S1 could not navigate most Pennsylvania trackage. Turntables were too short and curves were too tight. It could only run between Chicago and Crestline, Ohio. The shrouding trapped heat, and the duplex drive had balancing issues that caused wheel slip. Crews reported the S1 was spectacular but temperamental. The Pennsylvania Railroad retired it in 1944 after just 4 years. Lessons learned influenced later T1 duplex locomotives, but the S1 was scrapped in 1949. It proved that biggest is not always best, and looking spectacular does not mean working practically. Number 1. Beyer-Garratt articulated locomotives. In the 1930s, British firm Beyer-Peacock built locomotives so brilliantly designed for difficult railways they became legends in Africa, Australia, and Asia, while remaining largely unknown in Europe and America. The Garratt design was simple genius: 2 independent engine units, each with wheels, cylinders, and water tanks. Between them, suspended on pivots, sat the boiler. The entire locomotive articulated in the middle and could navigate curves that would derail rigid designs. As the locomotive consumed water and fuel, weight decreased on the engine units. The boiler remained heavy, keeping weight over the driving wheels where traction was needed. This delivered consistent pulling power. On Africa's lightly built railways, Garratts hauled trains twice as heavy as conventional locomotives without exceeding axle weight limits. East African Railways. 59 Class hauled trains weighing 2,000 tons over bridges built for 1,000 tons. In Australia, Victorian Railways H Class became the country's most powerful locomotives. Garratt complexity worked against them in developed markets. Maintenance required specialized knowledge, and they looked backwards. By 1960, most were scrapped and replaced by diesel locomotives. But in their time, Garratt solved impossible problems with elegant engineering. They proved the weirdest solution is sometimes the best one. And that's all, folks. These locomotives proved brilliance does not guarantee success. Sometimes timing matters more than engineering. If you enjoyed this journey through forgotten innovation, hit subscribe for more locomotive history. Here is another video I have specially selected for you. See you next time.